Modern infrastructure, from cloud servers and medical scanners to supersonic missiles, all relies on a single component, the semiconductor chip. These chips are the processing cores in your phone, your car, and even your washing machine. They are built from silicon, a material that allows us to manipulate electricity with absolute precision. This diagram shows how a semiconductor actually functions. A conductor, like copper, lets electricity flow easily. An insulator, like rubber, blocks that flow. A semiconductor sits right in the middle, which means its ability to carry an electrical current can be turned on or off. By controlling the flow of electricity, we can build millions of individual switches. When these switches are wired together, they form logic gates, which process data and store memory. This architecture is what allows a physical material to perform the complex calculations that power the digital world. Those switches are called transistors. Think of a transistor as a gate for electricity that can either allow current to pass or block it, representing a 1 or a 0 in digital code. For decades, computing relied on individual, physically wired switches. Today, the industry packs billions of these components onto a piece of silicon the size of a fingernail. This requires a feat of precision engineering. We have to reliably build billions of identical structures on a single surface, using light to pattern features that are smaller than a single human cell. The manufacturing process begins with a blank canvas, a perfectly polished circular slice of silicon called a wafer. To build on this wafer, chipmakers first add extremely thin coats of material in a step called deposition. Next, they coat that new layer with photoresist. Photoresist is a highly specialized chemical compound that changes its physical properties when exposed to light. Then comes lithography. Machines built by a company called ASML project extreme ultraviolet, or EUV, light onto the wafer. EUV is an advanced form of light with an incredibly short 13.5 nanometer wavelength, used to print the most intricate microscopic layouts. This light strikes the photoresist, exposing only specific regions to draw a pattern. After the pattern is projected, a process called etching removes the selected material to create a physical structure. Manufacturers then use ion implantation. Ion implantation is a process that fires charged atoms into the silicon to modify how specific regions conduct electricity. They repeat this exact cycle: add material, coat it, print a pattern, remove what you don't want, and modify the material, hundreds of times. A modern chip is an engineered three-dimensional city built layer by layer. The industry kept improving chips for years by simply shrinking these transistors. But as components reach the atomic scale, controlling the current becomes difficult. This leads to excessive heat and power leakage. So when you hear terms like a 3 nanometer or 2 nanometer chip, those are not literal measurements of the physical parts anymore. Those node names are generation labels tied to overall improvements in manufacturing process, density, and performance. To keep scaling down, engineers had to redesign the transistor itself into three-dimensional structures. This diagram shows an upgraded design called a gate-all-around, or GAA, transistor. GAA is a structure where the gate surrounds the electrical channel on all sides, improving control over the current flow. Because these structures are so small, even a single microscopic speck of dust can ruin the entire wafer. Fabs operate as highly controlled clean rooms with perfectly managed air quality and temperature. You are building billions of microscopic components simultaneously with near-perfect accuracy. That combination of scale and precision makes chip fabrication the most difficult industrial process in history. Once those billions of tiny transistors are built, the completed silicon wafer contains many copies of the same chip laid out in a grid. Those individual units are cut apart into core dies. A core die is the bare, functional block of silicon extracted from the larger wafer. But a bare die is useless on its own. It needs advanced packaging. Advanced packaging is the engineering process of protecting, wiring, powering, and cooling the raw silicon so it can actually function. Historically, packaging was just a basic protective casing. Now it determines how efficiently different chip components combine, directly driving the final performance and power efficiency of the device. It is the vital bridge that connects an isolated microscopic logic center to a macroscopic system that can communicate with the outside world. Because of this intense complexity, no single company does it all. One company designs the chip, another builds the lithography machines, another runs the fab to manufacture it, and yet another handles the testing and packaging. This extreme specialization creates a deeply interdependent global supply chain. It is an ecosystem so complex that no single country can fully control or replicate it internally. And yet this fragile ecosystem sits underneath our most critical infrastructure, from national defense grids to cloud computing and artificial intelligence. Controlling semiconductor production provides ultimate geopolitical leverage. Global industry, national defense, and the internet all function because humans can carve billions of microscopic switches into grains of sand.